Welcome to another of these sessions where we do a deep dive into the way in which your diode laser works. Now, in the last session we proved beyond any shadow of a doubt that your diode laser does not mark and cannot cut wood or card. When we scorched this card, all of a sudden I could make a 5-watt laser mark it, and yet that same 5-watt laser was also working across here and it couldn't mark it. So somewhere between here and here, something has changed about the property of this card to make it receive 455 nanometer wavelength energy. And here is the proof of it. A, it doesn't work, and B, it does work. And the only difference is I've done something to this card by heat treating it to make it more acceptable to creating a carbon film, which then starts eating into the surface. Now, like all great magicians, this laser technology has got the ability to let you see only what you want to see, not what's actually going on. And this humble black line underlies a lot of the deception that people fool themselves with when they're using diode lasers. Let me show you what this black line actually is. That regardless of what you see, it is not a black line. I can hear you saying, this guy is an absolute nutter. Look, I can see it's a black line. Now, you'll note on there that I've drawn two sets of black marks. One where the line is weakest and one where the line is strongest. Just to give you a perspective of what I'm doing, you can see here my microscope with two side lights on it. So starting off the weakest part of that line, you'll notice that there are some slight variations in the shades of brown that we can see on here. That's quite a dark brown just there. As we move towards the section that was more heat treated than this, you'll see that the colour all of a sudden starts to get quite a significant darker brown. It's not black. You saw it as a black line, but you can clearly see how the colour in the background here now has changed to that yellowy colour where I've scorched the material. So look, without making any other changes, I'm going to magically turn that black line into something else. We'll try and do it slowly so that you can see that I'm not doing any trickery. All I'm doing is rotating the line, difficult under this magnification, and all of a sudden that black line is not what you thought it was. And that's the magic of light. I've not changed the lights are still side lights, but this time those side lights are shining along the groove that I produced, not across the groove that I produced. And we know that that's a groove because if I change the magnification, and you'll see the carbon on the edge of the cut. Now this, remember, is the darkest cut. So those bits of carbon are not responsible for you seeing a black line. Although the surface is in focus, this is not in focus. But if I raise the table and bring this into focus, you'll see I'm going down quite a long way. And when I get to the bottom, there we go, look, there are the fibres at the bottom of the cut. So what you're looking at there is a very slightly V-shaped groove where the bottom is flattish and whitish, much the same as the surface here. So how and why do you see it as a black line? When I turn the line that way, there is no light getting into the groove to reflect off the surface so that you can see what's happening inside the groove. No light, no reflection, nothing for you to see. It's a black hole. And so it appears to be a black line, just because there's no light getting into the depth of that groove. It's as simple as that. Easy when you understand what's actually happening. But in reality, you now know that that line is not a black line. That's a very, very, very important lesson about laser cutting and laser engraving. Just because it looks like a black line doesn't mean to say it is a black line. Absence of light is always black, and so consequently you cannot have a brown absence of light or a light brown absence of light. it will only ever be absence of light equals black. So we now understand how that black line happened, purely because of the action of carbon allowing the light energy to cut into the surface. If I want to actually create a black burn line on the surface, is that possible? Well, the answer to that question is maybe. You can see all the cellulose wood fibres in the card, and on the edge of the fibres here we've got some black, which is carbon, and we've got a little bit of sort of staining around the outside, which could be brown. So we maybe have the possibility here of being able to just create different shades of brown on the surface of the material. You will remember that I scorched the surface of this material and changed it to a different colour, away from white to brown. And if I'd have allowed a little bit more time, I could have turned that brown darker and darker brown. I would have not have gone deep into the surface to produce that colour. How do we achieve that same effect with a laser beam? Because at the moment, the problem with the laser beam is it can produce black and it can produce no black. In other words, if we take a look at the bottom there, you'll see that that colour at the bottom is exactly the same as this colour on the surface. It only appears black because it's deep. Well, I did warn you at the beginning of this session that we're going to dig deep into the way in which the diode laser works. Not the machine, but the actual laser beam itself. So we've now got to understand how to make black and brown on the surface of a material without producing a deep groove. Here is a graph, and I keep stressing that word. This is not the shape of a drill. This is the shape of a graph of intensity at the focal point where your beam tries to do its work. Right at the centre of your focal point, you've got a zone of very, very high intensity. So here we've got very low intensity, but there's enough time for the carbon to form on the edge of the cut. Right? But once we start getting a little bit higher up the intensity curve, like here, what we find that we've got enough time to produce the carbon and enough time for the carbon to heat up beyond 3,500 degrees C and disappear like magic. With the diode laser, you can only do two things with it: turn it on or turn it off. And if it's on, it's always going to try and produce that shape. If I switch the beam on for just a very short period of time, let's just say 1 millisecond for the sake of argument, then I produce a burn which looks like that. If I turn it on for 2 milliseconds, I get a burn that's like that. And if I turn it on for 3 milliseconds, I get a burn that's like that. So you can see the longer exposure time I give the beam, the deeper it will cut. So when you're cutting, the beam is not standing still. So it won't do 3 pecks in the same place. It'll do 3 pecks in 3 different places. So the beam will never get as deep as I've shown with 3 pecks. There will be some difference between a complete peck on its own or an overlapping peck. So we're going to move away from the slightly false world of a wood analogue, i.e. card, into the real world of wood. Because what I want to do is find out what the shape or the power intensity distribution is within the beam itself. This was an easy task with a CO2 laser because I always got clear acrylic to help me with that task. I don't have that aid here with diode laser. We have wood, which doesn't damage very easily, and it damages in a rather strange way with a carbon aid. It has to produce carbon before it can start damaging the wood itself. 2 lines. The first line is running at 5% power. The second line, 10, 20, 30, 40, 50, 80, 90 for 99% power is the last one. The first black line, a PWM frequency of 5 kilohertz, which is the standard frequency that you'll be using on your diode laser. Now the second line, I can do something that you can't do. And I've changed my PWM frequency for this layer. There's a good reason, and I'll explain when we start analysing the tests. I'm hopeful that this is going to give me a huge amount of information for me to understand exactly what I bought. So we're now moving into the world of real wood. And the problem with real wood, it's not going to work the same as card. For example, when we look at the end of this wood, this is a piece of pine. And look, you can see the growth rings. Now those growth rings appear on the edge here, add different colours. But hopefully what I'm going to get is on the side here, I'm going to get some marks. So at the end of these very simple tests, I expect to be able to work out what the intensity profile is for this beam. Now I've got my focus, 10mm, which is the intensity focus for this wood. I'm using that word again, intensity focus, because there isn't such a thing as a focus. This spot size is supposedly the area through which all the rays pass. Do I believe that? Of course I don't. You'll clearly see the 10 hertz. There it goes. I mean, 10 hertz is low enough for you to see. This is 100%. And you'll notice there's no pulsing on 100%. Looks like a piano keyboard, doesn't it? At 5% power, we've just about been able to mark the surface of the wood here. Well, these marks on the side here don't mean very much at the moment because the laser beam came in across the edge. So what I'm going to do, I'm going to just very quickly sand these marks off so that we can see what the real profile of the beam is. I may be the luckiest guy in the world because I've just managed to do something that is almost unimaginable. It looks as though I've managed to get half a dot there, half a dot there, and half a dot there. So we can see what the dotty results are as opposed to the continuous 5 kilohertz result. Immediately there's something else that we can observe. We'll see this line across here of the grain, and you'll notice how that grain has caused a different burn. These are all supposed to be exactly the same focus, and sure enough, look, perfect focus, and then all of a sudden we start to get a wider burn, wider. At the beginning here we've got a thin line, and then all of a sudden it becomes thick and then back to thinner. Different molecular structures here which are burning in a different way. If that's the correct focus, is that the correct focus? Can I get that any better? What the hell is going on with this beam? Because surely if it's in focus here 5%, it should be in focus here at 100%. When we're running with low power, look at the width of the cut here. I'm going to guess that's around about 0.2. But look how the cut width grows as the power increases. Here we're probably at 0.3. Now we found that the focus was nominally correct at 10mm. Now, look at all this burn here. Does that mean to say that it's out of focus? Because the intensity profile at this point is no different to the intensity profile at that point. Perhaps this is the wrong focus for that power. So at 5mm a second with 100% power, here's the focus that we were nominally setting to. And as you can see, it's got a big wide burn. So let's change it to 12 and 14. Is there any significant change as we increase the focal distance? Is there any significant change as we decrease the focal distance? Well, the answer is yes, because if you look at that and compare it to that is a narrower beam than this one. The beam is narrower at this point here. And something else that's interesting as well. So there's my focal distance there, 6, 8, 10, 12 and 14. There was the nominal one that we said was the best one. But look, if we set it to 6mm, we appear to get maybe a slightly better burn on the surface, but look at the depth of cut. We're probably 50% deeper if we go to 6mm focal distance. Now, from the very first test, I've known that there's something wrong with the way the laser is set up or the way the laser is working. Because here's what a 100% 40 watt cut should look like. Just a nice clean line. None of this horrible wide black carbon V on the surface. We're going to investigate why my cuts are not like this. But there is another advantage that's actually come out of this, whatever this problem is, and that is that we can see that producing various shades of brown and black on the surface of the material is possible. So what's allowing us to produce this colour here as opposed to a deep cut? The intensity at this point, just like I did with my card, we're beginning to just brown the material, create a material change. As we get a little bit more intensity, we're burning a little bit deeper because of the time that we're allowing. We're still not producing much material removal. but the only material that's being removed and evaporated is this under the very high intensity part of the beam at the centre. I've got a pretty shrewd idea what the cause of this problem is, so let's go and investigate on the machine. Apart from a little bit of test work that you've been seeing me do with this laser head, I have had the window out of here, the little protection window, out once and cleaned it. I believe we've seen that on video. So let's take a look at what this window is actually doing now. Right, so here's the protection window. It's just a piece of glass. Wow, look what we can see on there. 4 lines. We've got 4 sets of laser beams which are focusing down to a focal point. As you can see when I shine the light across it, it's a pretty cruddy finish on there. We've managed to get some fumes onto the surface that have actually smoked the glass. I can see my finger through the back there. It's not terrible. And that, I believe, is the root cause of our problem. One of the things that Lasertree did when they sent me this head was to supply me with a spare window. And here is that spare window. As you can see, it's a nice clear piece of glass. See what the difference in the results are. This window is only plain glass, so I can do no damage to it by giving it a clean with some isopropyl alcohol. Can I clean the damage off of it? When isopropyl alcohol evaporates, it leaves a film behind, so we need a very soft tissue. Lens cleaning tissues are absolutely fine, or if you haven't got any lens cleaning tissues, soft toilet roll will be adequate. Because if it's good enough for your bottom, it's good enough for a lens. Don't use kitchen towel, because kitchen towel has got abrasive in it. Well, I've now removed the film, but what I haven't done is removed the damage that I've done to the glass. Look, I've still got my 4 laser beams there. So that's bad news. Okay, well, this is plain glass, and we know that this is likely to be wrecked, so I can't do any more damage. Let's see if I can remove the marks with acetone. Are they burnt in marks, or are they permanent damage to the glass? Well, the good news is it looks as though I have removed them from the surface. So they are literally just burnt on bits of smoke. And I have restored that window to full working condition. So what I want to show you next is not my secret stash of gin, which I don't like, by the way. This happens to be a smoke generator. Looks like water to me. Well, you're right, it is just pure water in here. And what I want to do is to show you what smoke really is all about. This clear liquid has changed to white purely because the air bubbles in there that are picking up, refracting the white light that's all around. The same thing is happening with smoke, but in reverse. The only reason you can see smoke is because there are solid or liquid particles floating around in the air. Now, I want you to bear that in mind when you see the next part of this testing. I think you'll now see the huge difference that that clean window makes to the cut. We've got none of this surface carbon. These look exactly like the demonstration cuts that we've seen. The question is, how or why does that window clog up so quickly? Now here I've got a series of freeze frames from the tests that you've just seen me do. But before we talk about what these images are and mean, we need to go through a couple of little thought experiments and a bit of an explanation. Now take a cup of water and put it in a freezer. Or take that piece of solid H2O, walk into your kitchen, put it into a saucepan and turn the heat up high. Close all the doors and windows and wait for half an hour. I think you can imagine exactly what will happen. The room will fill with steam. It's microparticles of liquid water which are suspended in air, and they are refracting the light and causing the room to look white, just like fog. It's smoke in a way, but the point is you took just a cupful of solid and you turned it into a complete room full of vapour. Because this is a thought experiment, we can do something rather silly. We can take a little mini stick of dynamite and put it on the kitchen table. We can light the fuse and duck, and within a few microseconds, apart from the bang, the room will fill with fumes. The difference is the speed at which you were able to fill the room with fumes. That's a very important concept, the speed of fume creation. You might say, well, how does that apply to my laser cutting? You are converting solid material into volumetric fumes. So let's take a look at a few of my dodgy diagrams. Here we've got a nozzle, here we've got the laser beam, and here we've got the material. And this little red piece here is a piece of solid material that we've turned into vapour. That vapour will tend to drift away like this. So the laser beam now is acting for a longer period of time, which means it's converting solid into fumes or gas very, very quickly. Some of this stuff will be going up vertically because, hey, this beam is not solid. It's just a beam of light. So there is no reason why these fumes can't go up vertically. And as they come out of this hole, they will expand and start exploding sideways. We've got our laser beam on and we're producing a parallel hole. So now, how can the fumes get out? They will have to come out upwards, shoot straight upwards, and as they shoot up, there will be a tendency for them to want to explode sideways. The laser beam is only a beam of light. These are solid particles and they've got velocity. So they want to travel up here in all directions like little bullets. Let's go back to the beginning. What we've got coming out of the nozzle is airflow. And as soon as this pressurized air from inside the nozzle escapes to the atmospheric pressure outside, it's going to do exactly what a balloon does if you pop it. It's going to explode. We're going to get a change of pressure from pressurized inside to no pressure out here, so this gas is going to expand. It's not going to go, as people imagine, in a little jet downwards towards here. So we've got this waft of air that's coming out here, and it is likely to be a waft of air that arrives at this point here, okay, because we do not have enough velocity to really force air down into this area. And even if it does reach this area, it's probably at such a low pressure that it's going to do very little to go into this cut. This is a fairly low velocity air stream that's coming out here, that's expanding, and yet up here we've got this little jet of micro bullets that are climbing up the beam and anywhere around here as well, and they can find their way up into the nozzle against the airflow that's coming out. And the deeper the cut, the more linear the upward flow is likely to be. What I've just given you here is a mechanism by which it's possible to put fumes onto my window even though I've got airflow coming out of the nozzle. Now you might not believe me, so that's one of the reasons why I've taken these freeze frames, because there's no other way that you'll believe that story unless you see it for yourself. So you remember, all this testing was done at 10 millimeters a second, or 600 millimeters a minute in your terms. We had the power set to 5%, 10%, 20%, 50% and 100%. Now I'll remind you yet again that power is not power. Power in this instance represents exposure time. These are all 40 watts with different amounts of exposure time to give the appearance of a power change. Now the first row of pictures here shows the naked beam before it hits the work. Now it is interesting to see that there is a sort of a little shadow on each of these results, which seems to indicate that there's some sort of peripheral heating taking place. You see the beam completely and it's not hitting the wood. And the other thing that I'd like you to note here, the beam starts off wide, comes down to a focal point, and then look what happens after the focal point. It starts to widen out again. By the time it gets to the bottom material, that beam, I don't know, 3 millimeters wide, that's a point that we're going to discuss probably in the next session. How an expanding beam can produce a thin parallel hole. So this next row of images shows what happens with your standard 5 kilohertz frequency cut. Because the damage mechanism for this is actually 5,000 little micro pulses per second, we're getting not very much in the way of what looks like explosive damage. This is more like steam damage. Remember, it took a long time to fill the room with steam because it was basically a slow action. As you can see here, we've got our cut, and the material is being exploded, but it's being forced out the end of the cut here, and you can see it even more with this at 100%. When we get to my 10 pulses per second, my burn is not broken down into 5,000 little pulses. My burn is just one hit. So I'm converting a huge amount of material very quickly. And you can see that effect here. I'm explosively pulling out a lot of material. I don't think that's vapor. I think that part there is actually plasma. That's superheated gas that's being heated up by the laser beam itself. You can see that the beam is actually quite a thin beam from all these previous results. Look at this. This is a huge thick beam here, and that means that this debris that's in here is going up and probably going up into the lens against the airflow that's coming out. And similarly here, look, you can clearly see it going up. Because I've had to stop the camera lens down, we can't see all of the detail that's happening in these pictures. We can only see the detail that's illuminated by the light that's been created at this point here. These are continuous cuts in from the edge, remember, and so there is an escape path for the expanding gas to come out the end of the cuts, as you can see here. That's not the case with these, because these are effectively dots. They're closed holes, and the only way for the fumes to exit those areas is upwards. As far as lens protection is concerned, the air assist doesn't seem to be doing very much at all. Probably for the lower powers it may well be doing something, but certainly when we get up here into the 50s and the 100% powers, the fumes are going upwards and they're just barging past the downcoming air. Now before you move on, it would be a good idea for you to stop the video, go back and watch these burn tests again. Study the way in which the fumes and the debris are forcing their way up past the air assist. You can see what I'm trying to describe much easier live than I can do with these freeze frames. Have we noticed how clean these cuts are? These lines. There's no brown fumes around these lines. They're clean black lines. Well, black lines, you know what black lines are now. They're not black. Anyway, these deep cuts have got no fume damage around the outside of them. That's an interesting observation, isn't it? Why is that? Well, we've got to remember what the cutting mechanism is for this wood. The laser beam hits the surface and it converts a little piece of material into carbon. That carbon glows white hot, 3500, disappears, and a piece of clean material appears underneath to be converted to carbon and evaporate. As you've seen from the previous images, we are getting an upward flow of vapor or debris, but that debris is not the same as the stuff that you produce on a CO2 laser. You're not producing the tars and the resins that result from the breakdown of the wood caused by different wavelength of light. This is just straightforward carbon evaporation, carbon evaporation, carbon evaporation. There are no brown fumes. Even though you may be blowing the fumes back onto the work, those fumes are not brown sticky tars as they are with a CO2 laser. I was blowing air down, blowing those fumes, potentially some of those fumes, back onto the work. There are no fumes there. So having air assist is not doing the lens any good, but it's not doing any harm to the work either. There's a positive advantage here for the carbon cutting mechanism. That isn't the reason why people want air assist. They think that air assist assists the cut. We've got debris that's being ejected from this cut at very, very high velocities, and the cut is very small. How much of this air, when you think about it logically, is going to get into that cut against this upward thrust of vapour that's coming out of the cut. So as we've seen, if it's an open cut, then the vapour, some of the vapour can go along the kerf and escape. There's going to be far too much upward velocity of debris to let any significant amount of air get into the cut. And if the cut is closed, which it will be for most of the time, there's absolutely zero of this air that can get into the cut. The only time that you want air assist to help your cutting is if you can do one through cut. If you've got somewhere out the bottom of the cut for your fumes to go and for your air to go, you can make them both go out the bottom of the cut, and you can probably improve your cutting action, because this debris, no matter how you look at it, is busy absorbing the energy that's coming in, because you don't get that light and that vapour and that plasma for free. Something has to cause it, and the thing that's causing it is the energy that's going into the material. You've reduced your cutting efficiency. You can see huge amounts of white light. And then you have to ask the question, why is that light white? Why isn't it blue? Well, the reason it's white is because carbon burns with white hot vapour and white hot temperatures, 3,500 degrees C. So just remember, with these cuts, we're not throwing small amounts of power at this material. We're throwing 40 watts at this material, regardless of whether we throw 40 watts in one little pulse or whether it's 40 watts is a multiple set of pulses along there. We're always using 40 watts. And it's the 40 watts of energy that's the thing that's damaging the material. The depth is caused by the exposure time. But we're always throwing 40 watts at that surface, regardless of the exposure time. And so that's how we can produce nice clean cuts, whether we're working at 100% power or 5% power. So these lines here were done at 5, 10, 20, all the way up to 99% power. And they were all done at a constant speed of 10 millimeters a second. Some of these are done with a PWM frequency of 5,000 pulses per second, and these were done with 10 pulses per second. Well, 10 pulses per second you can clearly see. You're going to say, well, what's the point of that? So let me explain the point of these tests with quick reference to the PWM diagrams. I'm never going to apologise for continuously reminding you that this diode laser has got no control mechanism at all on it. The only thing it can do is the same as the light that's hanging in the middle of your ceiling. It's either on or it's off. And the on and off is controlled by an electronic signal called a PWM signal. In your case, you can't even see the square wave here because they're so close together. There's 5,000 on and offs per second with your diode laser. Now, I've got the ability on my machine to do something that you can't do, which is to change the PWM frequency. And in this particular instance, I've changed the PWM frequency to 10 cycles per second. And I'm also running at a speed of 10 millimeters per second. So the maths is very simple. I'm going to get one pulse per millimeter, and the length of that pulse depends upon the power that I'm specifying. So if I specify 10% of the power, 10% of the time the light is on, and 90% of the time the light is off. When your diode is on, it does damage at a certain rate. If you only allow it to run for 1/5000th of a second, it will only do a certain amount of depth damage. If you allow it to run for twice the amount of time, it will produce almost twice as much depth damage. So the depth of cut depends upon the exposure time that you allow your beam to hit the material. In this particular instance, you're allowing the laser beam to hit the material in one spot for 5,000ths of a second, and then of course we're moving on at 10 millimeters a second, so within a short period of time the laser head has moved on, and the next spot that you put down is not the same as the first spot. So it won't be twice the depth. There'll be a difference between two burns in the same spot and two burns at slightly different spacing, whereas you're using 10%, 5,000 times a second, producing lots of little mini pulses that are spread over a millimeter. My pulse is not spread over a millimeter. Look, there's a millimetre. I'm getting my pulse all in one go. The difference between these two lines that we're producing, one a line of dots and one a more or less continuous line, is the exposure time that I'm allowing. So you wouldn't expect this to give as deep a cut as this one single pulse. Now, fortunately, I can just about get 5,000 cycles a second and the 10 cycles a second on the same screen for you to compare. You can see the depth of damage that 5 kilohertz has done as opposed to 10 hertz. The overall exposure time here did not do as much damage as it did here when you hit it all in one go. So let's move across to 40% power. We've got a smaller entry burn here because we've got lots of multiple pulses and not a very big beam width, because we're never allowing the beam to grow because the exposure time is small. Whereas here we've got a bigger beam width because we've allowed the beam to grow more because we've used a single pulse. And so the hole is bigger and the beam starts off bigger. But it's interesting to note that at a certain point they almost become the same diameter. And something weird is happening just across here. Look, all of a sudden the beam has changed diameter. And here we've got exactly the same thing. Look, as we look carefully, we'll note probably that the beam has not actually changed diameter. What's actually happened is the peripheral damage around the beam has changed. And that's an interesting clue which we'll talk about next time. Because, hey, we're getting into some fairly deep stuff now. Most people won't be interested in this, but to me, this tells me exactly how my beam is working. And what I can see here is, look, the beam is not a pointed beam. In both of these cases, it says the beam is very rounded on the end. This is not a Gaussian distribution beam, because if it was a Gaussian distribution beam, this point would be down here, like this, as a point. When we get to the next one, which is 99%, this is continuous 5,000 pulses a second, and this is continuous 10 pulses per second. They're both 100% power, and we can see that because if we take a look at the depth, they're both the same depth. But the thing that's not the same is the size of the burn. Look at my 10 hertz signal. Why the difference in these two burns? They're the same beam. This gets into very deep water about how a laser beam cuts, and we will tackle this subject in the next session because it's far too complex to tackle in this one session where I want to look at the shape of the beam, not how it acts and damages materials. We can see the shape of the beam from these pictures here. Look, the beam has got a round point on it. It's not got a Gaussian sharp point on it. This continuous line here at 5% and these holes here at 5%, but one every millimetre. If we take a look at the edge condition of this hole, you'll see that it has got a chamfered top to it, whereas this one has got a clean edge to it. These are details that most people would never even think about looking at, along with the fact that, hey, we've got this different grain structure here that's passing through here, and we've got holes with a certain characteristic here, and yet look at this hole. It's bigger and it doesn't have quite as much of a chamfer around the top of it. Minute details that tell me a great deal about what the beam is actually doing. And bear in mind, this is only 5% power, and 5% power is not producing dots. A dot is something that is black on the surface, not black because it's a hole. And at that magnification, I can see that those holes nearly 0.3 diameter. The chances of being able to do decent photo engraving with this head is nil. But as we looked along some of these lines, we saw possibly some little pits in there. That raised my suspicions because when I looked along some of these grooves, I saw what looked like a wall in there. Hang on, I should be seeing a groove right the way along. I shouldn't be seeing something in the background that was out of focus. So I decided to do a little bit more detailed investigation work. I took one of these grooves and I ground to within about 1 millimetre of the groove. With a scalpel, I peeled away what I could. Although that groove was, what, maybe another 2 or 3 millimetres deep, look, I could only get down as far as 3 millimetres, not 6 millimetres. The grinding disc has accentuated the different types of wood that are in this wood. So here's the cut line here, and you can see the different types of material. All of a sudden the material changes just here. We get a different width of burn. All this is carbon that's on the surface. Remember, this is the stuff that doesn't actually form a groove. It's just enough energy here to turn the wood into carbon, but not enough to actually burn a groove. And then here, look, we've got a nice cut, which as the material changes, look, it changes the width of the cut as well. And as you can see, there are many different changes taking place across this wood as it encounters different molecular structures. And what we can see there in the background now, that white section, it's nice clean wood where I broke it away. Here we've got a piece of wood, and here we've got a piece of wood, and here we've got a damn great big hole. So the cut is deep there, but shallow here. Note where these two lumps are on the screen, and let's just refocus onto the surface. And you'll notice how those two lumps are happening at this molecular material change. So this is a different sort of material which has got a different damage threshold. We shall see we've got lots of them. Holes, no hole, hole, no hole. We can't predict the depth of the cut because the cut on the edge said it was going to be this deep. But hey, you can see in the background here the wall that I was seeing. This is not a groove that's going straight back. This is a wall of wood that hasn't cut. Very, very bad news as far as I'm concerned, because if I want to do 3D engraving, it makes the 3D-ness very, very susceptible to the grain structure of the wood. I'm not going to get a proper 3D engraving if the structure of the wood is going to interfere with the power variation that I'm going to impart to produce the 3D depths. The more I look at this, the more I think I'm just doing experiments with a very expensive piece of kit that I've got no use for. Maybe other woods are slightly less sensitive. We will explore that possibility in the future. And the next time I'm going to try and answer the question, why did that happen? And also, with this rather exaggerated diagram of a focal point, several questions come to mind. Those two were done at exactly the same power and speed. Why are they different depths? And why are they different cut widths? And surely, when I get rays that are doing this, that are passing through the focal point at an angle, why don't the cuts come out like a dovetail? Why are they straight? Doesn't make sense, does it? Not unless you understand how cutting actually takes place, and very few people do. And next time I'm going to explain the mechanism by which you will get two different results from the same beam and the same speed. Until then, thanks for your time, and I'll catch up with you in the next session.